Thank you, GP, for the introduction, and thanks everyone for joining my presentation today. It works? I realized that it's Saturday, it's 3 p.m. We have temptation to do something else, but we decided to stay and listen about GANs, generated adversarial neural networks, right? So let's go. And my intention here is to dive deeper into one specific project we completed recently so that you could understand how we approach projects in AI and ML, how it may look like, and have a closer look on some unusual data sets here. Right. Yep. And as for the agenda for today, my second goal is to tell you a little bit about our artificial intelligence and machine learning capabilities here with EPAM systems. Because previously I covered mostly our data part. Then we will take a deeper dive into the project. I will describe the context, about the plans, about what we wanted to achieve, about the goals and constraints. I will describe our approach in terms of timelines, in terms of the team, and how we planned our effort. And definitely, since we are engineers, mostly here, I assume, we will pay some attention to machine learning techniques, neural networks, architectures, packages, different models, so sure, stay tuned. And if you have any questions, we have those. Right, my name is Anton Petrov. I have been with the company for 6 years already, and on events today, some speakers like to tell a little story about how they got into the company. So I wasn't really looking for a job, but when I took vacations and went with my wife to France, to a beautiful old city called Dijon, I was contacted by a recruitment team, and they described that they had some position. I decided to politely end conversation and asked to send email with job description. But then later I looked up EPAM systems on LinkedIn. I checked which data scientists they have in the team. I saw a good guy there, and I decided that if they have a good data scientist, most likely it's a good company. So, right, I sent them a cover letter with what was my past experience, what I'm looking for, that I see that you have a good person in your team. And I liked that when I went to the interview itself, they managed to reach to that particular person I saw in the LinkedIn. So he joined the conversation, and I had a beautiful experience. Right. I have been a long time with the company already, and I like this experience because we have different plans, we switch between different projects all the time, we get exposure to different technologies, and so although I work in a single company, I have an impression that I worked already in a dozen companies. I like it. And my specialty is on fast and impressive POCs or MVPs, like proof of concepts and minimum viable products. In artificial intelligence and machine learning, this technology is somewhat emerging. Some call it cutting edge or bleeding edge techniques, and it's always not clear what you will get on the output if you will invest some money into some R&D activities, right? So typically we start with the client with some short-term effort for 1 to 3 months to understand what we can get out of the data, what will be the value of the business, whether they want to proceed with this or not. So I enjoy during this short, focused, laser-focused R&D projects. And since I was on many projects already, I just naturally developed the expertise in different domains, working with different kinds of data, like tabular data, images, videos, textual data sets, and in this way I work with computer vision, natural language processing, etc. And this is what you could typically expect in the company, since we are changing the projects, we are changing technology, and data scientists, they're curious. They want to learn something new, look into new models, check new packages, and that's why typically our data scientists, they are generalists. They like to work with different stuff. Great. As for our machine learning capabilities, our plans are different. which means that our projects are different as well, but still I attempted to categorize them into several large groups. So the first group is about traditional predictive analytics for use cases you are familiar with, like fraud detection, churn analysis, revenue forecasting, etc. Basically, regression classification on top of tabular data. There is a lot of value in it. Like a lot of companies still didn't capture the value of traditional predictive analytics. There are lots of challenges here. And then some of our customers, they are building a sort of a marketplace when they have a huge inventory of products or content on one side, and on the other hand, and on the other side they have lots of users or consumers, and they need to match the supply and demand. And definitely, they need to solve this issue of long tail problem. And personalization really helps. We are happy to build a recommender engine for them, and typically such use cases, they naturally happen for clients from e-commerce or from media content industry. And then the last one is anything related to analysis of unstructured data. And this is pretty popular these days. Some of our customers, they have data in terms of images, texts, documents, videos, and they want to either convert this unstructured data to some structured form or introduce additional capabilities to their products so that the end users could enjoy working with such kind of data. Sure, we're happy to train one more neural network to solve the issue. They're pretty powerful working with unstructured data. Then, how we help our customers? On this slide, you have a pretty simple picture. It's a straight line from the beginning to the end. Later, I will explain that it's not that simple, but still. So first of all, we joined the effort, our ML team, not when we need to train some model, but much earlier at this step of pre-sale activity, when we just start working with the client, trying to sign a contract so that we can understand what they really want to achieve, and we start really educating them about what is possible with ML and AI techniques, because often they have expectations that we take a neural network and it will do everything. It will do everything, it will be perfect, it will be perfect and fast, efficient, right? So we joined the effort at the very beginning. Right, we meet with the client, with key stakeholders, we sit down with them, we do multiple whiteboard sessions, we discuss their constraints and requirements, we share our vision for what we'll build later, and in this way we have a pretty clear understanding of what should be the scope, or what should be delivered, and the customer is already on the same page with us, and they understand why we need a year deliver this functionality in not a month, right? This really helps. Then the next step is working with data collection, data processing. Everyone understands these days that for machine learning to happen, we need data, we need label data, we need probably large amounts of data, sure. And we help our customers not just move data from one place to another place, build data pipelines, build data storage, but also to label data. Because pretty often data is unlabeled, especially if it is unstructured. And we either help to build crowd-sourced labeling pipelines, or we even have a team in-house which label data all the time. This is their full-time job. And we manage to get label data pretty quickly with such things. Then it's pretty obvious what we do for models R&D. Our data science team, they can train a model, create it, deploy it, but most importantly, we pay significant attention to understanding what this model really does, in which cases it is applicable, where it works, where we can get value out of it, where it's not that well, and where it doesn't work at all. We just don't plan to deploy a model and see what happens, right? And as I already mentioned, nearly every single customer, they want to unpack this black box to understand what it really does, because no one wants to deploy a black box to production, rely on this black box for making their business decisions, right? No one wants to do it. Instead, everyone is asking questions, and we spend a lot of time not on just modeling exercises, it's pretty standard and easy to do, but on working with data and on working with stakeholders, building this trust, building this understanding, so that they could use those models efficiently by themselves, even when our team will leave the project. This happens sooner or later. And ultimately, once the model is ready, we don't leave the customer. We help to wrap up this model into some sort of a product or a service which could be deployed, which could be orchestrated efficiently, and actually already presented that we have MLOps blueprints, and we assist our customers throughout the whole process according to their maturity level. Some customers, they are pretty mature and they need a machine learning platform to work efficiently with machine learning technology, while other customers, they are just starting to work in this domain, and the approach should be completely different for them. And what's interesting here is that below, here, you see a list of logos, a list of unusual names. I won't go through all of them, but the key idea here is that whatever we deliver for a customer at the end of the project, it stays with them. And then we go to the next project. We cannot reuse the data we got previously. We cannot take the code, copy-paste it, and reuse it later. But this is IP. It stays with the customer, right? And we saw this multiple times that we often need to restart Unity from scratch. And in order to avoid this loss of time and effort and to reduce the amount of repeatable work, the company invests some time and effort into development of internal products, which we call accelerators, so that when the new project starts, we would prefer to reuse something which we built internally, right? And we gradually improve it, and in this way, new projects, we start them not from scratch, but from something which already works. And we even sell licenses for some products, like for Infra Engine, this NLP product which we have selling. Great. But now it's time for a deep dive to one specific example, to one specific project we completed recently. This project, it's just a random one I picked up. It's neither too advanced, neither too exciting, just random sample. And it was delivered for oil and gas company, and it's just coincidence that I actually talked about oil and gas customer as well. And what's interesting here is that I believe everyone really understands how to develop and deploy a model, let's say for an e-commerce company, right? How to conduct A/B tests. It's pretty straightforward. But when we are going to other more conservative domains like healthcare, security, oil and gas, there you cannot just continually deploy your models, right? You cannot conduct A/B tests by exposing end users randomly to your models. If you want to deploy a new model to, let's say, oil rig, you need to put a lot of effort here. And that's why this domain is pretty unusual compared to technological companies. On this project, our key stakeholders were geophysicists. They work with seismic data, and later I will explain what this really means. Basically, they spend the whole day looking on this data. They want to understand what happens below us, under the ground, whether they need to make it real to get some oil or not. This is their full-time job, and they wanted to automate it to some extent. They want to improve the data. They were looking on, because they spent the whole day looking into it. And what's also important is that this customer was actively transitioning into the cloud in AWS So ultimately we had two goals here. The first one is to develop some AI functionality, some AI features. And the second one is to partner with the client in their journey to the cloud. They wanted someone who already has this experience, so that someone could show them how to do this R&D in the cloud. They already had on premises multiple GPUs underutilized, and they wanted to transition to the cloud. So this is how it looked like. Their architecture is very simplistic. Actually, I already showed you a few architecture diagrams. So they had a front end, they called Petrov, and they wanted to put into the cloud with its nearly unlimited resource into the back end, where they could deploy some applications to work efficiently with their data. So for the end user, everything stays the same. They are working in the environment, while in the back end, everything exactly is happening. Right? So what is seismic data? What we are talking about here? First of all, how we are getting seismic data? On the ground or on the surface, they have either a machine or a boat which just goes from one place to another place. And on its journey, it makes a set of explosions. Those explosions, they happen every kilometer or so. They send sound waves below. Those sound waves, they propagate through the soil, they reflect back. And the speed is different in different mediums, right? You will have one speed in the sand, another speed in the stone. And in this way, once they collect the signal back on those sensors, they aggregate it, and they pretty much understand what happens many kilometers below our feet, whether they need to make a drill or not. So this is how seismic data looks like. Pretty simple. We are here above the ground. There is a vertical axis if you want to go below. There are multiple layers because the soil was formed differently in the history, and that's why we have layers here. And ideally, they expect that somewhere here they have good conditions in terms of pressure, temperature, and they can get oil out of it. Right. So on the input, we had not a table, but something which looked similar to an image. But this image was three-dimensional, right? And we expected that the average size was on a scale of 10 or 20 gigabytes with something like 1 billion values. But when we are saying that the typical size is 10 gigabytes, this means that actually we can easily expect that on the input to the ML model, we may get a three-dimensional data set of the size of 100 gigabytes. And we had a need to process it efficiently because end users, they used to wait a little bit to get their data on the screen. A second, a few seconds maybe. But if you need to wait a minute or two, 10 minutes, that's just unrealistic. So if you're curious how to process hundreds of gigabytes through neural networks, just go out, meet Svetak, he's a solution architect. He mentioned that he has a few design patterns for different cases, and he would be happy to brainstorm it with you. Then here I have exactly the same picture, right? And I can stay a little bit longer here. Maybe it looks familiar to some of you, like those red and blue colors. Maybe you have already seen them in Jupyter notebooks or in Matplotlib, right? Anyone? Anyone worked with Jupyter? Anyone is a data scientist here? I see one hand, I see another hand. Yeah, great. So in the break, if you want to talk more about machine learning, data science, AI, just feel free to get back to me. We can have a conversation. Right, but that's right. This picture looks familiar in terms of choice of colors, because it turns out that in Matplotlib, they have different color maps in terms of how to map different values of different colors, and they have just two divergent color maps with useful names, which are Coolmore and Seismic. So if you work with Matplotlib or Jupyter, you plotted some graphs, scatter plots, there's a good chance that you had some exposure to seismic data, right? So, right, how it was different from traditional photos, it was three-dimensional, and also there was an issue how to map this data to the screen, because one of the inputs you had a dynamic range of values from minus few thousands to plus few thousands. And on the screen, you need to map them to RGB with values from 0 to 255. And if you do just straightforward with the Python, your results, you won't notice those red and blue lines. Everything will be sort of blurred. And we were happy to have an SME, subject matter expert in the team, who really helped us to understand what we were dealing with, right? What we had on the inputs and what we had to provide on the output. Definitely, once our project is somewhat complicated in terms of data domain, we prefer to have SME, someone who really understands what we're dealing with. Then, this is how our inputs and outputs look like. In machine learning, we prefer to have inputs and outputs, so that this machine learning technique, this neural network, would be able to produce outputs with some inputs. So this is what we have in the input. Low resolution data, you see that you don't see what really happens here, right? The resolution is low. Here we have high resolution data, and our task was to produce high resolution output from low resolution output. And at the beginning of the project, we had similar understanding about seismic data. So if you don't understand what is on the screen, we were exactly in the same situation. Right, and why they needed it, if the resolution is low, they had expectation that something might be there. But once you get resolution in a higher picture, you may realize that really there is no oil there. You don't need to drill. And this is also why I like this project, is that although it may potentially save the customer some money, because they don't need to make unnecessary drills, but also it helps the environment, right? Because if you understand that there is no oil there, you won't make an additional hole in our plant. Right. In terms of the approach, we had two streams. We had a need to develop AI functionality. That's why we had a team of data scientists, like 5 people. Also, we needed to build some orchestration, deploy it to AWS with integrations with the front end. That's why we had developers as well. And this is, by the way, the only real slide I have in my presentation. I forgot to mention that our clients are sensitive to expose their IPs, to expose their data to someone else. So I completely anonymized my presentation. The data which you see here, it is from the public domain. I do not provide any metrics, any codes, anything what you can reuse. Basically, right? I completely obfuscated the presentation. And this is the only real slide, because I can share it. And by the way, this slide is taken from our platform, which we developed by ourselves. We sell this tool called Telescope AI to other companies who want to work efficiently with their people, and definitely you need to have it once you hit a few dozens of thousands of employees in the company with AI features, right? So this is an example of a product which we are selling. So, right, two streams, two kind of skill sets, distribution by geography. We prefer to have a team which is allocated in some time zone. In this particular case, they were from Eastern Europe. As for the technical skills, data science team, they are proficient with Python, data science. As for developers, that project is unusual because we had people with expertise in .NET. We don't have a lot of projects with artificial intelligence and .NET. So that was unusual. And in terms of seniority, this is interesting. At the very beginning, at 8 a.m., if you were still with us at 8 a.m., Sveta, he told that we have a B track for architects, for project managers, and sure, we have an architect and a project manager. We had for like lead developers, and we had for middle developers. So that was a team composition. Also, we had a junior data scientist on the team. That's why you see a light blue color here. Typically, you wouldn't see a junior person on a real project. Usually, they onboard them gradually, they participate on internal projects, they build expertise, and then later they need to be exposed to a real customer. And this junior data scientist, he was a really bright guy. As for the approach, this is where it is different from the beginning of the presentation. Initially, I told you that we have some initial phase about discovery, then we do data pipelines, then we do models, then we operationalize them and deploy them. This really never happens in practice. You don't need to do this sequentially. Because your data pipelines, you will always need more data. Your machine learning models, you will always need to retrain them and get better accuracy. Instead, to complete everything on time, within a short period of time, we launched everything in parallel. So we started with the first discovery phase, setup of the environment, scope understanding. This is what we really needed to do in the very beginning. But then, we did everything in parallel. Data scientist team, they can build models, they can build modeling pipelines, they can build some prototypes, even without the data. You know, machine learning engineers, they don't need to get a final model from the data science team before starting to put it to AWS environment, right? They can do something with similar models and then update them. So we launched everything in parallel, and in this way we managed to complete our objectives in time. And also you may see red colors here. Those correspond to public holidays. Since our team was distributed across different countries, sure, at the very beginning, our project manager, he collected all information about public holidays when the team won't be available. So in the company we have good work-life balance. We don't work on holidays unless we really want to. Let's go now it's time to discuss another project. And since we're talking about resolution enhancement, I believe it's pretty easy to build an analogy with what is being done for traditional photos. Let's say from your smartphones. I just saw those smartphones here, right? I believe you already saw those applications when they can take a photo of low resolution, like on this picture, apply some bilinear transformation, get better resolution, but still, it's pretty blurry, sometimes not that useful. Especially for this particular customer, because when you're working with photos, you do it by yourself actually, and you don't really care. But geophysicists, they're professionals. They have a lot of stories when an error in one single picture had a cost of millions of United States dollars for a customer. So they looked into nearly every single pixel in our output and expected an accurate results. And this is how GANs work. Having this input, they produce such output, and we're curious whether we can use this technology, those neural networks, generated adversarial networks, retrain them for this particular data domain, for seismic data, and then get this result into the output. It works for traditional photos. Can it work for seismic data? Everyone was curious. But those GANs, they're popular. Actually not. They're not popular. They're very difficult to train, to maintain. So this is a niche technology, but when it is being used, it produces exciting results. So I have a few examples here. Like in Photoshop, they use GANs for some exciting neural filters. NVIDIA, they develop a few tools about how to use GANs to speed up rendering three-dimensional scenes in gaming. Right now, many gamers have huge screens with high resolution. They want to build complex scene, and there are prototypes where you could first render a scene with low resolution, apply again, and get a three-dimensional scene with high resolution. This is exactly what we did, but with seismic data, not in gaming. As I already mentioned, there are a lot of challenges why training GAN is difficult. But basically, the key challenge is that neural networks, they're difficult by themselves. They're complicated, you need time to train them. Then, once they're trained, you need to find a way how to improve them. But this is a black box, so it's difficult. For GANs, you need two neural networks. You need a generator and a discriminator. So how they work? Right, you have two neural networks. The generator, it generates high-resolution data out of low-resolution data. It generates data. While the discriminator, another neural network, it takes on the input real data sample, and also it takes on the input some generated data. And it tries to understand which data is real and which data was artificially generated. So two neural networks, one generates data, another one tries to understand whether the data is real or not. They compete with one another, they try to outperform one another. That's why we have adversarial in the name. And basically that's all what you need to know about GANs, unless you are a data scientist and AI practitioner. Right, and why it's difficult to train them? Sure, you have two neural networks. You have one challenges. The obvious one is that you need to store them in memory. You need to have more computations. You need to manage two computational graphs. That's pretty obvious. There are some ways how to do it. But what about this computation challenge? They are competing with one another. And what will happen if one neural network will outperform another one? The result won't be good, because the second neural network, which is inferior, it will not learn anything. It's a loser, right? So once those neural networks they're not balanced, once they're not learning from each other, you're not getting any result. So you need to constantly be aware that you need to balance the learning process of two neural networks so they could learn from one another. And there are lots of other challenges here. I will skip that. As for ML technology stack, in a team we often have debates about which tools to use, which programming languages, which packages, right? And later Jamie will tell you a bit more details about the choice of programming languages. In this case, it was pretty straightforward. We used Python. And we had 5 data scientists on the team. So once we met each other, we had to decide what to use. There were multiple deep learning packages, frameworks which we could use. PyTorch, TensorFlow, they are limited in this market, but there are other ones, like Paddle from Chinese companies. Can we use them? But I was excited to see that on this particular project, we had an agreement within the team. When we met, everyone just said, let's use PyTorch. Right, TensorFlow was outsourced, open sourced by Google. A lot of time already ago. It's pretty efficient, but let's use PyTorch. We used both frameworks before we liked the latter one better, so let's just use it. And also what I like about such R&D projects is that the technology is pretty new, and the customer is looking for someone who already has experience with it. And we have this ability to choose what we will really do. And the customer is happy to hear from us why we made such a choice, which challenges we had with alternative options before, right? Right. So we decided to use PyTorch, and just for your information, I just saw that not all of you are data scientists. So artificial intelligence, it became pretty commoditized these days. Any one of you can go to the GitHub, clone some repository, and get those GANs on your laptop. You can apply them to your pictures and get exposure to this technology. But when you will decide to try to do something on your own, if you want to do your custom neural network, you don't really need to start with low-level language like PyTorch and TensorFlow. There are some high-level alternatives. And what I want to talk about here is PyTorch Lightning. And this is a package which we use. If you work with low-level code, with PyTorch, for example, you need to constantly make decisions about what to do, where to put your neural network, to CPU or to GPU. You will constantly rewrite the same code all over again across your projects, and gradually you will become tired of it. And also you will need to make a lot of design choices, like you have a class for your model, but how to train this model? Do you need to write a function, or do you need to write another class? How to work with data? Do you need to write a function which just reads this data, or do you need to write a class which basically does the same? And how to manage those classes of functions? Should you put them into a single file, or should they be separated across different files? So the choice of design is really important. But if you are just beginning, or in reverse, if you have a lot of experience and don't want to do the same choices all the time, you can use what PyTorch Lightning offers you to do. Basically what it does, it shows to you how to organize your code effectively. There are other options, but this one works. It allows you to avoid rewriting the same code all over again, which is low level. And we have a few codelets here. Let's go over them. We are engineers, right? So here there's an example how to write a neural network with PyTorch Lightning. And it's pretty straightforward. First, you create a class. You define how the neural network looks like. You need to define what are the layers, what it consists of, whether it will be about recurrent layers or convolutional ones for images. Then you need to define how to propagate your data through it. I realized that the code here may look pretty complicated, but it's pretty simple. You just take your data, you put it through your layers, and you collect your data back. This is what it really does. And then you need to say how to train this neural network. Where your data is stored, what is the format, so that the model will take the data, take inputs, take outputs, create and optimize or calculate loss functions, and learn from this Lego data. This is really what it does. So the main key takeaway message here is that it's great